Good morning, ladies and gentlemen, and welcome back to functions, I guess, with in pre-calculus. This is Resh Mahaber signing on from Wayne State University. Just wanted to go ahead and talk a little bit about. Excuse me, I'm a little raspy this morning. Talk a little bit about domain and range, and this seems to be the hardest thing for most people to really get their bearings around. So we're going to talk about domain. Well, more domain, less range, right? Range is just all the things we can get out, but we're more interested, just in real life, we're more interested on the things we can plug in. And of course, I would say if you didn't watch the functions video, to go back and watch that before you actually watch this one, because this one is for sure going to be an application of that stuff we learned about inputting stuff into functions. So without further ado, let's get started. All right, so when we talk about domain, right, one thing you have to keep in mind, I drew this picture last time, so I'm not gonna, well, I guess I will draw it again. Here's your inputs of your function. Here's what the function does. Don't know what it does, but then it shoots out the output, which is f of x. The point is that all the things we can plug in is called the domain. Now, this is super important. And why is this important? It's kind of like driving your car, but putting battery acid in your gas tank. Okay? Obviously, if your car is the function, if you put battery acid in, you're going to break your car. It just makes really good sense, right? That you'll break your car if you do that. Or if you poured a gallon of milk into your gas tank, that obviously wouldn't work. It's not in its domains of the function, which is fuel types, okay? So you have to really think about this thing when we start talking about it. And many different fields have different domains for the things we work on. As a matter of fact, when we talk about sending emails, if you don't type in the correct email address, the function, which is your email provider, will send you back a message that said was not able to send message. Okay, that's because you gave the incorrect input. Okay, so domain and ranges are important, but more so the domain is so important because it tells you all the things you can possibly plug in. All right. So without this being said, let's zoom in a bit. That's a lot of bit. All right, and let's really get started here. Okay, so when we talk about domain and we have a picture, I think it's easier to find a domain, but let's forget the picture right now. Let's just talk about how we find a domain with, let's say, a function. So let's say, for example, my function is find the domain. I'll put the instructions right here. The domain of this guy. X squared plus 2x plus 4. And remember, what are we trying to do in this problem? Find the domain, which means find everything that we can possibly plug in. So now this is where I'm going to have to put some perspective on things. If I asked you, what do you like? You're the function. What do you like? Answer the question. And a lot of you are probably thinking right now, well, what do you mean, what do I like? List every single thing that you like in the world. And obviously, for some of you who know what you like, that's going to be an overwhelming question because chances are there's a lot of things out there that you like, right? But those of you who haven't experienced a whole lot, you're probably saying, well, what if I experience something I do like? So it kind of shuts things off. Well, what if I said, what do you not like? Tell me what you don't like. I'll tell you right now, I don't like mayonnaise. I don't like gloves. Okay, so there's specific things I do not like, right? So what does that mean? In my domain, instead of looking at all the things I do like, right? So let's say this is everything in the world. Instead of looking at all the things I do like and try to highlight all those, I'm saying don't highlight all those at all. Let's just pinpoint the crap I don't like and take those and throw them out. And what I'm left with inside of here will be my domain. That's the goal, because there's just so much stuff, especially when we start talking about numerical inputs. There's an infinite amount of things. What are you going to do? Go through and analyze every single number on the number line? It's impossible. So we need to look at what's called a function's domain restrictions. So here we go. So every function has one of three domain restrictions, okay? The first one I'll talk about, and this should make really good sense. What's the one number you can't divide by? Everybody should have said 0. So what does that mean? That when you divide your denominator, which is the thing you're normally dividing by, the denominator, one thing that would break our function, so this is our domain restrictions. The denominator cannot be equal to 0. This number 1, the entire sentence is what you need. The denominator can't be equal to 0. What's something else can you not do in the real numbers? Well, a lot of you should have said that we can't take square roots or even roots, as a matter of fact, of these kinds of numbers, right? Because square root of negative 4 makes no logical sense in the real number system because it gives you imaginary stuff. So bottom line is, if you have an even root, okay, anybody know what the name of the thing underneath the root's called? It's called a radicand. Okay, the thing underneath the root. So a little bit of vocabulary. This thing is called the radicand. Okay, and most of the time I will abbreviate it as rad. The radicand cannot be negative. This thing can't be negative. And if he cannot be negative, what can he be? He can be either positive, which means greater than 0, or equal to 0. Because those are two things that if you're not negative, you're either positive or you're 0. Done, right? And there is a third one. The third one, actually, I'll give it to you, but I won't put any examples with this guy in it until we get to later on sections in the book. Because I like to cover this when I cover logarithms and exponentials, because I feel like it's very, very pertinent with solving equations. But anyhow, so this one I'll write in a different color because we won't have any examples with these in it. Okay, that is, if you have a logarithm, the base is written as a subscript, right? The answer is already in your face. The answer to a logarithm is always going to be the exponent. But if we have a logarithmic function, there is constraints on this guy as well. What's the constraints? The argument, the b, must be strictly greater than 0. And we'll talk more about this in the future. That's why I didn't want to talk about it now, but I'll give it to you because all three of them do exist. So if you get a function with a logarithm, you need to be saying to yourself, there's something that is fishy here that I can't do. Alrighty, so I gave you this problem, right? And I said find the domain. Well, here we go. You need to start going through a checklist in your head. When you start thinking domain, you think, oh, okay, what are my restrictions? Well, let's see, what's the checklist? Do I have any denominators? So you start saying to yourself, denominators. Do you have any? Nope. So what does this mean? In your head, and what's the mentality? We start with every number on the real number system, and we look for bad stuff, we throw them out, and then what we're left with is our domain. So right now, I started with all real numbers with this function. Denominators, it doesn't have any denominators, right? And so therefore, I'm not going to have any restrictions on it. Done, gone. All right, so therefore, I'm still at all real numbers. Do I have any even roots? Obviously, another no. So, what is the moral of the story? The domain of this guy, which I'll write like so, okay? Some people just put a D in a colon just to make it a domain, but is all the numbers on the real number system. So I always like to say draw a number line to represent the real number system, and I'll shade in everything for all the numbers that happens. So this is everything, which is negative infinity to infinity, and this is my domain. Real simple, meaning this guy has no restrictions. He likes everybody. Okay, or you can do the cheap mathematician's way, which is all real numbers. Okay, so that's basically it. If you know these three restrictions, right, then you can find the domain of any function, no matter how freaky it is. So this is the basics of it, right? So let's do some basics. So this was the basics. Let's talk about the example. Okay, so let's do example 1. So this is example 1. And I'm going to do an example with all of these in them, so you can actually get a feel for how this works. For example, okay, I already wrote example, I'm going to write it again. Let me give you a different function that we're going to find the domain of. F of x equals the square root of x plus 4 over x. Okay, and this is kind of me jumping the gun a little bit. Note, you don't have to have just one restriction inside of these guys. You can have multiple, okay? But here is the brass tacks, okay? And maybe I'll even write this so everybody can see this. Okay? For each restriction, there will be a problem to solve. Okay, so what does this mean? Once again, what's my checklist? Denominators and even roots. Do I have a denominator? Obviously I do, but what should I do here? Denominators cannot equal 0, right? But let me make this denominator a little harder. Let me make it x plus 1. And why am I making it x plus 1? Because this thing says, what did I do? I did something. Oh, duh. My big hand clicked on stuff. All right, so denominators cannot be equal to 0. So this is my entire denominator. Substitute this thing in for the word. So x plus 1 cannot equal 0. Done. Can you solve that? I hope you can. If you can't, you need to look at my beginning videos on how to solve equations. Remember, mathematics is a pyramid topic. If you don't understand something else, you're better off not moving on. So what does this tell me? This function does not like everybody. He is very, 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 very biased against -1 for whatever reasons. Meaning that -1, if you plugged him in, he makes the denominator 0, right? Because that's what we set up the restriction to be. And when it makes the denominator 0, we're dividing by 0, which is garbage. But we're not done yet. This is just the first restriction. We have one more restriction, and that is even roots. Yes, which means the radicand must be greater than or equal to 0. Question, what is the radicand in this problem? And don't you dare snatch the entire root when we're just looking at the thing on the inside. It's just going to be the x plus 4. So x plus 4 must be greater than or equal to 0. Question, can you solve this? Yes. Okay, so this is going to be x is greater than or equal to -4. Now note to yourself, this is where things can get a little complicated, and I'm going to put a very complicated example in this in about 30 seconds, where I use a really, really freaky looking function and I show you all the different techniques. And what am I going to refer to you as? Note, if this inequality was nonlinear, once again, go back and look at video 1.8, which talked about how we make a sign chart and solve nonlinear inequalities. We're going to need a sign chart in order to solve this. Okay, it's not just a straight up push through. Okay, so please, 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 please be careful. So now we have a problem here. We have two restrictions. Who do we listen to? One guy says, I like everything bigger than -4. But notice, everything that's bigger than -4, and I'll draw you a little picture here, and then I'll erase it out. Here's -4. We're bigger than -4. But notice, this guy says, I don't like -1. So they're contradicting each other. He likes somebody that he doesn't like, and he likes somebody that he doesn't like. So who do we listen to? Well, think of this. They're in the same family. They're in the same function. They serve the same purpose. If you have siblings and you've ever had to share with them, you kind of understand what I'm talking about here. What was the number one thing your parents told you had to do? That is compromise. Okay, you can't be in a relationship or have a relationship or exist with somebody or work with anybody if it's all your way. You have to compromise. So what does this mean? That everybody has to get what they want. Okay, so here we go. Here's my analogy. Here's how this is going to go. So once again, so what did we do? Let me draw you a little picture of what we did here. 1. Each restriction. Now, what did we do with each restriction? We solved each restriction. Now note, in this problem, I only had 2 restrictions. Will I always have 2 restrictions? No. And you'll see in some of these examples, I can have 22 restrictions, and then that means I'm going to have 22 problems I need to solve, and then I'm going to have to compromise the Brady Bunch because it'll be a giant family of restrictions, and everyone's going to be picky, and I'm going to have to give everybody what they want without contradicting people. Okay. Now finally, what I'm going to have to do is marry or compromise the 2 together. Compromise the 2 restrictions. Now, here's something that's interesting. When you compromise the 2 restrictions, here's the big key. The big key is understanding that how do we do anything? We start with somebody, and then we get somebody else's opinion, right? So we start with ourselves, we get our own opinion, and then we snatch out the other, then we get someone else's opinion, and then we snatch out and find a compromise between those. So I'm going to start with this guy, because he's very moody. He says x must be greater than or equal to -4. So I'm going to draw a number line to help me figure all this out. Okay? So he says this. Okay? Makes good sense. Now this guy, on the other hand, says, that's nice, but I don't like the number -1. So here's -1. So what does that mean? He can't come. If he can't come, it's kind of like, it's kind of like having a roommate. It's kind of like having a roommate. Let me draw this again, guys. Sorry. Um, it's kind of like having a roommate, and he has friends. So all these guys, and we don't want -1. And he has friends that we don't like. The friends just can't come over, or he has friends that eat all his food. Like, his friends just can't come over. So what we're looking at here is everybody that's greater than -4 except for -1. This is our answer. So this is going to be -4, including hard bracket, all the way, keep going until -1, soft, union -1 to infinity. This will be our domain. Done and done. It is fairly simple once you get the hang of it and you create yourself some structure. You know, structure is the biggest thing in mathematics, okay? So, let's go on to a bigger and better example. I'm not trying to run the video too long, but I want you guys to get an understanding of how freaky these things can do, or could become, all right? Let me give you one that is a little not nastier. Okay, so this is example 2, and I'm always going to try to do 3 solid examples in every one of my videos. They give you a bunch of variety. So here we go. All right. So you look at this and you're saying, well, what are our 3 restrictions if we're trying to find the domain? Do we have a denominator? Yes. Do we have an even root? Yes. Okay, so we have stuff to do. Even roots here, denominator is the entire thing. Now, I catch a lot of people saying, oh, if the denominator and the even root are in the same place, we can do something magical, right? Which is set things strictly greater to 0. I'm going to encourage you never to do this until you have developed why people do this, okay? So mathematics, in a sense, is kind of like learning a rule book. You learn a rule book, but then when you get really, really good at playing the game, and because you follow the rules for so long, you start to realize that certain rules are bendable, okay? And a bendable, in a sense, means that you have a redefined understanding, and you understand that some steps in every process can be skipped or can be shortened if you have the mental intellect to do it. Until you gain this mental intellect, I'm going to tell you to not do this. There are 2 restrictions here. And if you don't know what I'm talking about, then good for you, okay? Because I've seen a lot of bad habits in people. So let's solve each restriction. Denominator cannot be equal to 0. So that means the entire denominator, which is this, cannot be equal to 0. And likewise, even roots. Notice the radicand must be greater than or equal to 0. What's the radicand here? Well, the radicand is just the crap that's underneath the root. It's really that simple. Like, don't try to make things harder than what they are. Einstein said mathematics was around to make things easier, not more difficult. Alrighty, now can we solve both of these? Now once again, what are we doing? Step 1, we labeled all of our restrictions and we're solving them. So solve each restriction. So I have 2 problems here because I had 2 restrictions. This video is going to run a little bit longer, guys. I'm just letting you know. It's going to be, because there's one more example I'm going to have to do that I'm going to end on, and I don't want to end on a high note. I want to put an example at the end of this so you guys can actually see. You can see what I want you guys to do for the next video. Anyhow, so this ends up being this, and that ends up being that. So what is this saying? This is saying that x is greater than or equal to 3, right? So once again, we're done. Now let's compromise the 2. Now the math way of saying compromise is intersect, meaning that what they have in common. But I feel like that's so inhuman. That's not real life. Here's 3, that could be equal to 3. All of that, right? Here's 12. But I don't want 12, have issue. Now, will they all look the same like this? No, but this just happens to be what this one looks like. So here we go. This is going to be 3 to 12, soft union 12 to infinity. Here's our domain. Easy. All right. Let's take a second and look at some filth. All right. So brace yourself, guys. Here's a good one. All right. So here's a really good example for you guys to take a look at. For example, Okay, g of x, let's find the domain of this guy. X minus 3 over square root of x squared. Put a minus 2 out here. I'm making this up as I go, guys, so you're going to have to bear with me for a little bit. Minus 2x. Don't make this a 2, make this a 3. I think that works out better if I make it a 3. Minus 3x, and I want you to put a plus, plus the cube root of x minus 1, right? And then, just for good old giggles, e to the x. Oops, I hit my big thumb, hit something. E to the x. Now, what is this going to do? Well, once again, even roots of denominators. Oh, what the heck? Let's put some dirt in here. The square root of x of 7 minus x. All right, the problem's finally done. Okay, so how many restrictions? So let's do first things first. How many restrictions do you see? The biggest key to all of this is identifying all the restrictions. Now, I'm not going to write denominators can't be equal to 0 and even roots must be greater than or equal to 0. You should be able to already identify that. If you can't, go back and watch the last two examples, okay? So denominators can't be equal to 0. How many denominators do we have here? Well, let's put our two problems. Denominators. You notice I always start by saying denominator can't be equal to 0. Well, here's one. Here's my first denominator. So square root, the entire guy, this thing, minus 2, cannot be equal to 0. All right, let me put another problem up here. And yes, I can solve this, but you'll notice structure is more important than doing the mathematics. What's the other denominator? Denominator can't be equal to 0, right? So this ends up being the square root of 7 minus x cannot be equal to 0. Done. Oops. Yeah, the entire denominator. Now, what's our next one? Even roots. So, do I have any even roots? And then if I do, the ER will say that the radicand must be greater than or equal to 0. So how do I diagnose whether or not something is an even root? Well, a square root, a fourth root, or a sixth root is an even root. A cube root is considered an odd root and has no restrictions. Why so? Because I can do a cube root of a negative number. For example, cube root of negative 8 is negative 2. Simple answer. It's not like it's not possible. It is very possible, right? The domain are all the things that break our machines. They won't break the cube root. The cube root's good for any number out there, okay? And because this is negative 2 times negative 2 times negative 2, which equals negative 8. So obviously all this crap is not important, okay, as far as the cube root goes. So it's just even roots. So where do I have an even root? Well, I have an even root right here, all right? So that means 7 minus x must be greater than or equal to 0. Some people are already looking at this saying, something looks familiar. Okay, and then last but not least, we have another even root, and that is the radicand must be greater than or equal to 0. This is our fourth restriction. Notice we have 4 restrictions in here. Okay, we have x squared minus 3x must be greater than or equal to 0. All right, guys, so what do we got to do? Let's get to solving. All right, this one's going to be a longer example. This is going to be probably another couple minutes on this video, guys. I apologize. I know I said I was going to keep them under 20 minutes, but I can't stop mid-example. Isolate, square it. X squared minus 3x minus 4 cannot equal 0. So x minus 4, x plus 1 cannot equal 0. So x equals 4, that can't happen, and x cannot equal negative 1 can't happen. So here's two numbers that we don't like. Bingo. Let's do the same thing here. 7 minus x cannot equal 0. X cannot equal, that's negative 7, so x cannot equal 7. So we already got 3 numbers we don't like. 4, negative 1, and 7. Can I solve this one? Yeah, this is an easy guy. So you notice after a while, solving these becomes almost like a rhythm. So the first thing was identifying our restrictions. Second thing will be solving them. And then the third thing would be mirroring or compromising them together. And now look at this one. All of you should be good with this if you watch my other videos. What do we need in order to solve that? We need a sign chart. And why so? Because he is non-linear and and inequality. And I talked about this in great deal in my video 1.8. I would encourage you to go back and watch that as a review if you do need a review on how to make a sign chart. So what do you need? You need to figure out when this function right here is equal to 0 and when it is undefined, which some of you guys call bad numbers. Okay, so when is it equal to 0? Well, I don't know. That's when x, let's factor this, minus 3 equals 0, so x equals 3, x equals 0. Okay, when is it undefined? Well, that's only when denominators are equal to 0, right? Hence why it's undefined. It's kind of like our domain restriction, the denominator can't be equal to 0. So we have none of these. So let's draw our sign chart finally. Note, a sign chart is a number line. Okay, then what do we do? Okay, but it helps us tell us where it's positive or negative because we're looking for when it's greater than or equal to 0. We need to plug stuff in for each one of these quadrants. Quadrant 1 is, I'm going to pick a number that lives in here, -1. And after you do the math, you'll see that this is -1 squared, which is 1, minus plus 3, which is just 4. So this is positive. And just skipping the math, because I'm really trying to get to the nitty-gritty of the problem, which is mirroring it at the end, and bringing out one other point. This is going to be negative, and this will be positive. And these are zeros. And note, we're looking for when is it greater than or equal to 0. So, when is it greater than or equal to 0? It's greater than 0, positive, between here and 0. It's equal to 0 at 0 and at 3, and greater over here. So that's going to be our answer for this guy. So we got 4 answers. So you notice these problems can be really, really involved if you're not, for each restriction that you get, not if you're not anything. Okay, so we have 4 restrictions. We solved each restriction. We identified them. We solved them. Now let's compromise them. All right, guys. So this is what I'm going to do. Let's finish the problem out. Now, what do we do when we do 4 things? I want you to multiply, and this is going to sound random, but I want you to multiply. Okay, 5 times 2 times 6, and give me an answer. Go. All of you probably said 60, right? But you didn't multiply all 3 together. You multiplied 5 and 2 together, got 10, and took 10 and multiplied it by 6 and got 60. Well, this is the same kind of thing. We need to do 2 at a time. We can't do all 4 at once. So let's do this one for number 4. Okay, since he seems to be really elaborate if you look at this picture. He says 0 to 3. I like 0, right? And then I like all this crap. I like 3, and I like all this crap, right? Now, watch what this creature comes along and does. This creature comes along and says, that's nice, but I have a problem. I like 7 and everybody back. So I want you to look and see what they have in common. And if you're paying attention, you'll see that what they have in common is from here to 0. Notice that here, it's just the red line. It's not the black line. So therefore, there's nothing here that they like. And 3 all the way to 7. This is going too far. So what we're looking at is the marriage of the last 2 restrictions. So our new number line after we do this should look something like this. Okay, so we have 0, we have 3, and then we have 7. Okay, so that's what we're left with. And that's just marrying the last 2. Oop, I did a lot of skinning. Just give me 1 second, guys. Let's get back in frame. Yeah. Okay, now, so that's check and check. Now it says I don't like the number 7. I don't like the number, well, I'll just do I don't like the number 7. Oh, look, so I just don't like this number. Boop, gone. 7's gone. That's easy. I don't like the number 4. Boop. That's not -4. That's where 4 lives. Boop. Gone. And then I don't like the number -1. So you see, the more restrictions, the more people that are in your family, the more issues we're going to have, right? And that means the more marrying you're going to have to do. So now, what are we going to do here? Well, let's write our domain. negative infinity to negative 1, soft, union, negative 1 to 0, hard, union, 3, hard to 4, soft, union, 4 to 7. This is our domain. Okay? It doesn't get much harder than this, guys, all right? So this is as freaky as the problem gets. And notice we had to use all of our solving techniques to get there. So I'm going to encourage you to always keep grinding to find the big things. Okay? So for class tomorrow, okay, solve this guy. Or, I'm sorry, for a good practice, too, if you guys need to. And you can look back at the video. Solve this guy. Find f of x equals, right, the square root of 6 minus x all over the fourth root. Well, let's make this a fourth root. All over the square root of x squared minus, let's see here. Minus 9 minus 4 plus e to the x. I love throwing exponentials and stuff. I don't know what that is. All right, guys. Find the solution to this, and I'll see you in class on the flip side. Remember to go somewhere and to do some things you've never done, guys. You're just going to have to step out your comfort zone and start pushing past and evolve. So grow, and I'll look forward to seeing you guys on the next video.